Okay, thank you, Tasho. So my job is to review some developments on Eisenstein series since Corvallis, or something like that. So first of all, So let's start from SL2. We have the hyperbolic upper half plane H with action of SL2R. Thank you. And the automorphic space is H mod SL2Z, let's say. And there are auxiliary important spaces closely related. One of them is H mod N, where N is the upper triangular matrices, which is just basically a line, but the measure is dy over y square. And then there is H mod gamma infinity, which I'll call Y, which is a cylinder, but again, the diameter is 1 over y at height y. And we have maps from this H mod gamma infinity. Gamma infinity is just the intersection of gamma with n. So we have a map from y to x, because gamma infinity is contained in gamma, and a map from y to z, because gamma infinity is contained in n. And the second map is proper. The fibers are just circles. So this picture shouldn't be unfamiliar to you. And one can define a constant term by, let's say, from functions on x to functions on z, by first pulling back to y and then pushing to z. Oops. Sorry. Yeah. I guess there is some lag here. So this is the constant term map from functions on x to function on z. So by the way, I gave the file to the organizers if they want to put it in the Dropbox so that people can follow. They're more than welcome to do so. If I had some competence, I could do it myself, but I let other people do it. Okay, so the function space in question, well, it could be locally L1 functions or N infinity or smooth functions, but it cannot be compactly supported, because compactly supported don't, after this, they are not compactly supported necessarily because of the first map. Formally, the adjoint of this operation, of this operator, at the level of compactly supported function on z, remember z is just the line, you take the sum over gamma mod gamma infinity of f of gamma of z. And if you're compact support, then you're still compact support after this operation on x, on H mod gamma. Now, unlike x itself, which, of course, that's what we are after, that's the most important space, the space z is more kind of benign, but it has more structure because it still retains the structure of left action, left multiplication by the torus. Remember, z was H mod n. Yes? Okay, good idea. Chalk here. So here is good. So x, script x is H mod gamma. Gamma is SL2Z. And then there is the y, which is H mod n. And n is just 1 star 0, 1. And we have z, script z, which is H mod gamma infinity. And gamma infinity is gamma intersection n. So you have a map from here to here and from here to here. Good. Now, at first approximation, the theory of Eisenstein series wants to kind of spectrally expand this map because there is an action on T on the left-hand side. Sorry? Okay. If I make some stupid mistake, please let me know. Oh, sorry. Yeah, I'm always going to do these mistakes. Thank you. Okay, switch. But just the order, not the letters. Okay, so that means in particular, or essentially, you start with not a compactly supported function on z, but rather on an exponential function on z. and you want to make sense of of this thing. And that's what Mass did way back in the 40s. So he considered this sum of imaginary part of gamma z, gamma acting by Möbius transformation to the power s plus half. It's always convenient to normalize it this way, over the constant gamma mod gamma infinity, which you can identify with integers, primitive lattice elements in Z2. And you get this expression. And this is, of course, similar in shape, and in fact, you can make it more precise, to what Eisenstein really considered. Eisenstein was born 199 years ago, by the way. So he considered modular forms where instead of S you have weight K and you have a holomorphic function in Z, but this is just real analytic in Z, but it has S as a continuous parameter. And this Eisenstein series converges for real S bigger than half, and it admits meromorphic continuation and a functional equation relating S to minus S. And these Eisenstein series, they form eigenfunctions under the Laplace operator, and they give you ultimately the non-discrete part of the spectrum of L2 of X with the action of the Laplace operator. And the theory was developed by Selberg and then Langlands in full generality. And when I was a graduate student deep into the last millennium, somehow people thought that Eisenstein series are the whole theory is very complicated, and certainly the literature was not easy to look at, let's say. It wasn't easy on the eyes. And well, in some sense it's still true, but things improved a little bit. Anyways, one thing I will mention, although I will certainly not get into that, the Eisenstein series are not limited to arithmetic lattices. The theory is kind of analytic. You just need the rough geometry of H mod gamma. Of course, in higher rank, lattices tend to be arithmetic anyways, but the theory is not, the level that I will explain is not analytic, is not arithmetic, rather. Okay, so in the 1980s, Joseph Bernstein came up with a new idea to meromorphically continue the Eisenstein series. He sent a letter to Petetsky-Shapiro explaining some principle which he believed that would give the analytic continuation. And so it is based on some soft principle of meromorphic continuation, which I will explain. And I think that the main feature is, it's always in mathematics that progress is somehow to overcome some psychological barrier. So it avoids the role of L2 of X, which is somehow, of course, Eisenstein series, the raison d'etre is to do the spectral expansion of L2 to furnish it, but for the meromorphic continuation, you need to kind of forget about the L2, at least the L2 in the strict sense. So Langlands referred to it as the bed of Procrastes. So for those who don't know, in the Greek mythology, Procrastes is some villain who puts his passers-by in some bed, and if they are too short, kind of stretches them with a Smith hammer. If they are too long, he amputates their feet. And if they fit exactly, then he has another bed of a different size. Anyway, so it's better to avoid the L2. That's the moral here. And in fact, no real spectral theory is used in Bernstein's proof, beyond very basic Fredholm theory, which is even not pertaining to Hilbert spaces, but to Banach spaces. I will explain. So my first goal is to explain this Bernstein's proof, which is fortunately now kind of available on the archive at least, and then I will try to explain the spectral decomposition, how we understand it. That's for today. Let's see what happens. Okay, any questions so far? Okay, so let me turn to Bernstein's proof, and I'll start with the digression with this principle of meromorphic continuation. So, oops. Yeah. Before that, I should make an important remark that with this Eisenstein series that I described, the mass Eisenstein series, you can easily normalize it by considering not just primitive points of the lattice, but all the points of the lattice, non-zero, of course. What you will get is just a multiple of the unnormalized Eisenstein series by this zeta of 2s plus 1. But the advantage of this normalized Eisenstein series is that you can easily analytically continue it, in fact, and study its poles. There's only one pole. And that's the same proof as Riemann gave 180 years ago or so for the Riemann zeta function. And what you get is a functional equation after you multiply by these Archimedean factors. This is Euler's gamma function. You get a precise functional equation, and as I said, you get control over the poles. So that's, of course, very advantageous. The problem is that this method is too special. Maybe I will say something about this tomorrow, but it's hard to make this kind of naive idea work in general, kind of in full generality. We don't know how to do it. The Bernstein's proof is different. It doesn't use, as I said, there's no arithmetic there. And the disadvantage that it gives less. It doesn't give you full control of the poles, it just gives you meromorphic continuation. So in particular, it gives a different proof of the meromorphic continuation of the zeta function. But as I said, without information on the poles, the poles of the unnormalized Eisenstein series are connected to zeros of Riemann zeta function, so this certainly doesn't give you anything about that. Okay, so now let me turn to Bernstein's proof. And so first I will just explain very kind of general things about analytic functions in locally convex topological vector space. Most of the spaces will be Fréchet spaces, but just for the bookkeeping, you need a little bit more. Anyway, so an analytic function for me is just a weak analytic function. So I'm talking about analytic function from, let's say, C to the n or some complex analytic manifold to a topological vector space, locally convex, so it's defined by semi-norms. And so weak analytic means that if you apply a continuous linear form, then you have a scalar function, and then you just want this to be analytic for any continuous linear form. But in fact, in all reasonable cases, this is equivalent to the stronger notion that you have Taylor series, convergent Taylor series, or Cauchy's theorem, or all the things in complex analysis, they continue to hold in this generality. So this is a very, very standard thing. Actually, Grothendieck, when he was a kid, he has a paper from the 50s, I think, or 40s on this kind of issues. Yeah, and one thing to somehow is different in the intuition that this notion, it implies continuity, for instance, but it's not very sensitive to the topology. I'm not going to make it precise, but it's really a more kind of flexible notion. Okay, and of course, once you have analytic functions, you can speak about meromorphic functions. This just means that after you multiply by a scalar function, it becomes analytic. So typically, you start with a complement of a closed analytic set, let's say in Cn, and you want to extend it, so it means that around every point, you can find a function, an analytic scalar function that after you multiply, it extends to this neighborhood. Okay, so that's the notion of meromorphic function in a topological vector space. And in particular, we can speak about analytic functions in linear, in the space of continuous linear operators from one topological space to another. And it doesn't, as I said, it doesn't really matter what topology, but let's say pointwise convergence. And that means that the matrix coefficients of these operators are analytic in the usual sense. One thing to observe is that if you have composition of two analytic families of operators, then by Hartog's theorem on separate continuity, separate holomorphicity rather, then the composition is also analytic. So these are just some basic things. And now we come to the notion, again, elementary notion of analytic system of linear equations. So what is it all about? So a system, we will present it just as some operator So we have some set of indices I, and then mu I is some operator from this space V where you want to solve your equation to some space ui. And we write an equation like mu I of V is equal to ui are some fixed vector. This is the non-homogeneous part. So sometimes you just look at linear functionals, but in practice, these equations are usually given by operators. But of course, you can always apply linear functional. It will be the same data. And we will write sol of xi, this letter is xi, I guess, is a set of solutions of some affine space. So this is just linear algebra, but we will have some topology. So in practice, the space V and ui, so I call them calligraphic E and calligraphic Fi, they are housed of locally convex topological vector space, and we require that this, now the ui and mu and ui now depend on an extra parameter, so let's say in Cn, and we require that depend analytically on a parameter. So in practice, I mean, it's very clear what I mean. This is just to make this formal. So I have this family of operators depending analytically on S, and these are the equation mu I of S at V is equal to uis. For so each S I have a family of linear equations, and this family is analytic. So for short, and I'll call it ASLE, analytic system of linear equations. And it doesn't really matter, as I said, if it's operators or linear functionals, but in reality, it shows up as operators. So this is this notion of analytic system of linear equations. I hope it's clear enough. And so it has nothing to do with automorphic forms. And what does the principle of meromorphic continuation says? Well, it says that if you have such a system and somebody tells you that there is a unique solution for some open set of parameters S, then this solution, let's call it V of S, then Vs admits meromorphic continuation. That's the principle. So principles are not theorems. Principles, they are better because you don't need to prove them, but they're worse because they are not always true. So to make it true, you need to put some conditions. And I don't think it's clear what is really the right condition, but there is one condition which will certainly make things work, and that's, but maybe it's a bit strict, but anyways, it's good enough. So we say that this system is of finite type if I can kind of a priori put the set of solutions, some affine space which depends on S, I can put it in some finite dimensional space which varies analytically in S. Okay, so this is what, and is for technical reasons, it's good to have this injective. So I have some fixed finite dimensional space and an analytic family of linear operators but when I say operator, I always mean linear and continuous. Here it's finite dimensional anyways. But anyways, so I have this continuous family, or analytic family of operators from L to my space where I look for solutions, such that the solutions kind of are a priori inside this image. That's the notion of finite type. And of course, once I have finite type, I can speak of locally finite type. And that's, okay, that will be called LFT. And so the basic theorem, which is very easy to prove, in fact, is that if you have an analytic system of linear equations on a topological vector space, which is locally of finite type, and the set S, where the system has a unique solution, let's call it Vs, has a non-empty interior, just in the usual topology, then this set, in fact, is open, and the complement is a closed analytic set. V is holomorphic on this set, and it is meromorphic on Cn. That's the theorem, and in fact, I think it's not very complicated to formulate, but the proof is in some sense easier than the statement. It's just some application of Cramer's rule, because you can kind of locally put this system just as a usual Anyway, this is just basically an algebra. The finite type somehow makes it all easy, but nevertheless, it's a powerful principle, and the fact that you can get something like the Meromorphic combination of zeta s out of this principle, I think is striking. Okay, any questions so far? Okay, now let's go back to, before we go back, well, we have to check some conditions of the locally of finite type. So how do you check locally finite type? We also have to check uniqueness, of course, but what about the local finiteness? So the kind of the easiest way to come up with system of locally finite type is Fredholm theory. So what is a system of Fredholm type? This is just ad hoc definition, if you like. So suppose I have two Hilbert spaces and two families of analytic operators between them, mu s and nu s. Suppose that mu s is a strict embedding. Strict embedding means that the norm is basically the same after mu s than before. And nu s is a compact operator. Then I claim that the homogeneous equation mu s equals nu s is locally finite type. So this is, of course, just a variation of the usual theme that, the identity minus a compact operator is, finite rank, etc. Not finite rank, but the kernel is, the kernel and co-kernel are finite dimensional, rather. So basic Fredholm theory, and the same argument proves that. So that's a very kind of basic fact. And it's really a statement about Banach spaces, not so much Hilbert spaces, but I formulate it this way. So that's kind of the easiest way to concoct systems of locally finite type. And in practice, how do you check that an operator is compact, let's say between Hilbert spaces? So again, the easiest way is to show that it has a stronger condition, namely that it's Hilbert-Schmidt. The formal definition is that the sum of the square of the norms of AEI, where EI is an normal basis of H1, is finite. This doesn't depend on the choice. But in practice, if you have, as in most cases, an operator from, let's say, one Hilbert space to an L2 space, then, well, you cannot evaluate this at every point because it's just in L2, but you can evaluate it almost everywhere. And if this evaluation is a bounded functional, and the norm of this functional is in L2, this is equivalent to saying that the operator is Hilbert-Schmidt. So that gives a practical way to check that an operator is Hilbert-Schmidt and therefore compact. Okay, now let's go back to automorphic forms, and again, SL2. So I will recall some notation, but I'm not sure if I... I don't know if I should put everything on the board, but okay, maybe the important things. So I will have this space, f of UMG, function of uniform moderate growth. Oops. Now you see why I don't like to use the blackboard with my handwriting. Anyways, so, well, it means that the function and all its relevant differential operators, they are bounded by some y to the n, at least for y bigger than, let's say, y half. And the Eisenstein series certainly gives you a function of moderate growth when it converges, but the growth depends on the s, or on the real part of s, because you have y to the s. So that's why you need to deal with all these spaces together. So this is the space that we want to solve our equations. And what are the equations? So now I will write to you the equation that the Eisenstein series satisfies. So there are three of them. So let's go over them in detail. So the first equation is that if I convolve So psi is the solution that will be the Eisenstein series. So if I convolve by a function h, so to make sense of it, because I only deal with functions on G mod k, I need the function to be by k invariant. So this is meaningful. And this will be, so the claim is that under all these convolution operators, the psi is an eigenfunction with an explicit eigenvalue, which is just the eigenvalue of this function, y to the s plus half, because I just average, so this commute, so it will still be an eigenfunction after I average. And this function can be explicitly computed. This is some kind of Selberg transform. I mean, the space is also very concrete. So there's no mystery here. The second equation, what's written here, so this is the constant term of psi. Now it's a function in one variable. And I want to say that what this equation says is that it has a y to the s plus half in it, and then it has some constant time y to the minus s plus half. I'll write it in the next board more explicitly. So this is what this equation says. So this is kind of the non-homogeneous part. So it's, maybe I'll just show you. So it's y to the s plus half plus something times y to the minus s plus half. But let me just switch back. And the last equation says that psi is orthogonal to all Cas forms. That just comes from the jointness. Of course, this is the pairing. So these are the equations. One has to digest them a little bit. So the convolution equation, the equation about the constant term, and orthogonality to the Caspidal spectrum. And now I claim that I can apply the PMC, the principle of meromorphic continuation, to this system. But first of all, I better check that the Eisenstein series satisfy this. Well, this is kind of routine. So as I said, the second equation just means that the constant term is y to the s plus 1 plus something. And I don't need to know anything about this something. That's kind of the beauty of the proof. This something turns out to be some quotient of zeta function, but this is kind of besides the point. And the other equations are straightforward. And now to apply the principle of meromorphic continuation, I need to know two things. First of all, I need the uniqueness. For real s bigger than half, the Eisenstein series that we wrote down explicitly is the unique solution, not just it's a solution, but it's the unique one in the space of function of modular growth. And the second, and that's actually, so the uniqueness, you only need the last two equations, and the first two equations give you the locally of finite type. So let me just give you some details about the proof. I mean, what I want to convince you is that the meromorphic continuation of Eisenstein series is a simple thing. That was not clear when, as I said, when I was a graduate student, let's say. So how do we prove this? Well, the first thing, so here is the statement. The claim is that if I have a function of uniform moderate growth on H mod gamma, and it satisfies these two conditions, so this one says that it's orthogonal to all Cas forms. This one says that the constant term is y to the s plus half plus something times y to the minus s plus half. The TA involves normalization here. The claim is that if I'm in this region, then this must be the Eisenstein series. So these are just the two last equations that I rewrote, and the conclusion that I get the Eisenstein series as the unique solution. So, and it's easy to prove, but the proof, I think it's kind of more than what meets the eye, but let me just write all the steps of the proof. Hope it's possible to follow this. So what do we need to show? We need to show that this solution is the Eisenstein series. Let's take the difference and show that it's zero. So I have a function of uniform moderate growth. Because I killed the non-homogeneous part, it must be, the constant term is proportional to y to the half minus s. That's what this condition will tell us. And because it's proportional to y to the half minus s, well, that means that it's bounded. The constant term is bounded for y bounded away from 0. But for functions of uniform moderate growth, we have the basic fact that the growth is controlled by the constant term. So the difference between the constant term is rapidly decreasing as y gets large. So if this is bounded, the constant term is bounded, then the function itself is bounded for y bigger than 1/2. Now comes the step, which is like in chess, we put like exclamation mark because it's like a very important step. So psi prime is bounded for y bigger than half, but now I claim that psi prime is bounded on the whole of x, because this set contains oops, I lost my chalk. But this set contains the Ziegler set, right? So this is a fundamental domain, and so it contains something. It's contained inside y bigger than half. The half is, of course, not so important. So the function is bounded on the whole space X. That's kind of the key step. And once the function is bounded on the whole space, then the constant term is bound, right? The constant term just taking the integral from 0 to 1. So now I get that the constant term is bounded not just for y bigger than half, but on the whole positive line. But remember, the constant term was proportional to y to the half minus s. So now, if I go for y close to 0, I will get that it must be 0, because y to the half minus s is not going to be bounded near 0, because real s is bigger than half. It's not equal to half. So the conclusion is that the constant term is 0. Okay, so one has to digest this argument, but it's a very nice argument. And once the constant term is 0, that means that psi prime is cuspidal, and now I finally use the third condition to get a contradiction. Any questions? Okay, good. So this is the uniqueness part. Now let's go to the local finiteness. So the local finiteness, as I said, one uses Fredholm theory, but as a very simple Fredholm theory. So, but for that, we need another small idea, which in some sense we already used. So it's easier to work on Hilbert spaces. That's a way of life. But the Hilbert space is not, you have to work with many, but of course for each S, it's kind of a fixed Hilbert space. So the way to do it is to approximate this complicated space X by a simple space, which is just this kind of rectangle. So a truncated cylinder, truncated Z. So we have this Z. Oh. Now I guess, did I switch notations also? Okay, so this is now Z, sorry. And which was Y before, I'm very sorry. And now I just truncate it from below. And I have the projection, I restrict the projection from Z to X to S. And when I restrict it to S, then somehow when I'm high up, this is 1 to 1. But if C0 is large enough, small enough rather, then this will be onto. So I kind of model my complicated space. I mean, it's not good to view this space as fundamental domain, but let's just kind of crudely think of it as a fundamental domain. I just put it in a nicer space, or a simpler space rather. And I can just work on this space. So this space is much more friendly. And in particular, I can consider Hilbert space. So here it's a weighted Hilbert space. So it's not a unitary representation or anything, but it's just a Hilbert space. And it gives rise to a Hilbert space on X. Just by pulling back the function, I get a Hilbert space with a strict embedding to Hn of S. So this is a weighted Hilbert space of X. As I said, it's not a unitary representation, but it will be actually a representation of X. Well, in this case, it's K fixed, but you can morally think of it as a representation under G. And the function of moderate growth, if you like, by definition, is just the union of the smooth part of these Hilbert spaces over N. Okay. And the good thing about this space Hn of the Ziegler set is that you can do a very simple analysis by just decomposing a function. So you still have the constant term. It's a meaningful operation. And you have an orthogonal decomposition of a function to its constant term, and, well, the difference, which is cuspidal in the sense that the constant term is 0. This should not be confused with cuspidality in X. This is kind of a more simpler notion. Because to be a cusp form, you need that somehow all the constant terms, for all y, not necessarily bigger than something. But this will be good enough, and that's easy enough to work. So you have an orthogonal decomposition of this Hilbert space to functions which are just constant. So again, this S is just like array times a circle. And you just do this, decomposing functions on the circle to constant functions and functions with integral 0. That's nothing more nor less. So this is a very kind of naive operation. And now, I admit that it's a bit hard to follow the first time you see it, but I'll just try to give the idea. So the idea is that I can consider a system on this Hilbert space, the weighted Hilbert space of X, which consists of the following equations. So I just modeled the equations on this S space. So what do I do? So the last equation, well, this is kind of homogenization of the equation with a constant term. So of course, this is a consequence of the equation of the constant term, but I now don't care about the first term, I just care about the exponent, so this will certainly be satisfied. So this is the last equation. The first equation, of course, just comes from the fact that it's an eigenfunction under the delta H, but now I only project it to the cuspidal part in the naive sense. So I pull it back to S, my function on X, I pull it to S, the Ziegel set, and I take only the cuspidal part. Now the point is that, I mean, why do I need to do it? I mean, the equation would be true without projecting to the cuspidal, but the problem is that the convolution operator is not compact. I want a compact operator. I'm willing to pay a lot of price to get a compact operator, so cuspidal projection tend to be a compact operator. But I still want to retain something, namely, so what about the non-cuspidal part? Well, I will just retain that, so this equality again is true regardless, because I just use orthogonal decomposition of two things, so both parts are equal, but I only restrict it to a segment of size A squared. So A is just some fixed number bigger than 1. So this will certainly be true. This will be a consequence of the previous equation, which I just broke the delta H F equals H hat SF to two equations. And the second one, I just took the homogeneous part of it, so to speak. And the claim is that when I write it this form, so again, I did this bizarre thing of projecting to the cuspidal part, and the other part I just restrict to a compact set. So, oops, goodness. So just, yeah, so there's a compact, I just restricted it to a compact part of this infinite, whatever you call it, rectangle. So the claim is that when I write it in this form, now it has the required form that, so I purposely wrote it in this way. So the left-hand side will be a strict embedding, and the right-hand side will be the Hilbert-Schmidt. So what is the strict embedding? I take the cuspidal projection, I take the constant part, but only restricted to this compact set, the constant part restricted to the compact set, and then I take this difference equation. And the claim is that this will be a strict embedding. It boils down to something very simple, which will be in the next slide. The other part, I have the cuspidal part after convolution. These things are Hilbert-Schmidt. And the constant part I just restricted to compact set, that will certainly be Hilbert-Schmidt. And 0 is also Hilbert-Schmidt. So that's the statement. And it's a very simple statement. Because the first part, the fact that it's a strict embedding, this guy, if you just write it down, what it means is the following very simple fact, that if you look at a weighted L2 space of the positive reals with weight e to the minus 2rx, r is just some parameter, and you perform the following operator. So you have some difference operator, f of x plus 1 minus lambda f of x, and then you just restrict it to 0, 1. So it is an injective operator, obviously, because if you know f of x1 plus 1 is equal to lambda f of x, it's enough to know f on 0, 1. But in fact, it's a strict embedding, provided that e to the r is bigger than absolute value of lambda. It's a very elementary fact, and that's all what it entails. While the second statement about Hilbert-Schmidt, again, that's a very standard fact that cuspidal part is Hilbert-Schmidt.
Can you go back to the previous slide?
Yeah.
So for the first operator, is there a h? Do you have an h hat there somewhere? Or you don't?
Right. So here I assume that h hat of s is not equal to 0. So that's why I can claim that it's of Fredholm type. So that's why the more precisely is.
No, I just wonder how come h hat of s doesn't appear in the breaking up of the two parts.
So I guess I just didn't put it, but it amounts to, I could have put it, it wouldn't matter as long as h hat s is not equal to 0. So that's just. So all what I need to know that I have enough h's so that h hat of s is not 0, but that's of course very easy. Okay, so I think that's all I want to say about the SL2 case. And but the nice thing about that, once you put it somehow in the right order of things, you just have to say the things in the right order, then the proof basically of SL2 has most of the ideas for the general case. The rest is just some kind of bookkeeping, which of course there is some, you have to get used to it, but we're big boys, so, and girls. So, okay, so I'll sketch the general case for those of you who are still could are not completely out of it. So I need to put some spaces in question. So, okay, G is now a reductive group over a number field. I fix, let's say it's split, and I fix a minimal parabolic. Omega is the Weyl group, a maximal compact subgroup. And then these are the interesting spaces, XP, GA mod UA, PF. These are kind of boundaries of XG, which is GA mod GF. That's what we're really interested in. And okay, this will be the notation for the Iwasawa decomposition. And delta P prime will be the set of simple roots. So there's still chance to put the file on the Dropbox, maybe if it helps people. Okay, and what we are after is this Eisenstein series. You start with an automorphic form on XP, and you form this series for any character of MA mod MA1. MA1 is the usual thing. It's just a vector space of dimension, the corank of M. And it converges for real lambda in some cone, and we want to analytically continue that. If you haven't seen it before, then I'm afraid this lecture will not help you much. But the instruction was that I can suppose all of Corvallis is known by everyone, so I don't know. Okay, so now we come to the key property that we use. In fact, that's basically what we use about Eisenstein series, and that comes from a computation of the constant term. So it's just like in the SL2 case, just more bookkeeping, but the same concept, Wuha decomposition. And the bottom line is that the cuspidal exponents, which I will not define, they are given very explicitly, or at least an upper bound for them is given very explicitly, by taking, so lambda is the spectral variable that the Eisenstein series is defined with respect to. So you translate it by the cuspidal exponents of the form phi, which we don't assume anything except that it's an automorphic form, and then you do some double-to translates. In principle, you have to take all the double-to translates by, the double cosets of W mod WP mod WQ, but because we take only the cuspidal exponents, it's only certain W's, namely those which, after you conjugate M by them, contains L. So the details are not too important. I just want to give the feeling of things. I mean, it's in my notes, which I hope to modify at some point. So this is the key property that we're going to use. As I said, it's just some kind of global version of the geometric lemma of Bernstein-Zelevinsky, which appeared implicitly in the previous talk, by the way. And how do we make an equation out of this? Well, this is basically a system of linear equations, but we need just one small piece of information, namely that, so in this computation you get all these intertwining operators which somehow are very important, but they are swept under the carpet. The only thing that you need to know is that the term corresponding to the identity element in the double constant decomposition, which actually is only there if Q is contained in P, otherwise it's interpreted as 0, it will be the constant term. So in other words, if you look, so the previous system was homogeneous system, but now I make an inhomogeneous system by saying that when I subtract this cuspidal part of the constant term along Q, if Q is contained in P, then what I remain with is all the other exponents with W not equal to the identity. And the claim is that this already suffices for uniqueness. So this strange-looking property determines the Eisenstein series as an automorphic form, well, at least in this region. So it's the unique automorphic form, so that when you take this difference, you can say something about the cuspidal exponent. So again, one has to digest it a little bit, but it's very similar to what we have to SL2 in principle, just that there's, of course, as usual, more notation and things to worry about. That's the uniqueness property, which somehow controls it. But in fact, it follows from something which is, so you can forget about Eisenstein series for a moment and just consider automorphic forms in general. So there's the following uniqueness property for automorphic forms. Let's read this. So suppose I have an automorphic form on xg at GA mod GF, which is not identically 0. Then the claim is, so first of all, Lagrange tell you that there is some cuspidal exponent. It's almost a tautology, but it's a very kind of conceptually important statement. But now I claim that, in fact, you can find the cuspidal exponent along some parabolic, where the real part, after you translate, so it's really the unnormalized exponent, they lie in the closure of the positive Weyl chamber. So you're always guaranteed to have some exponent in the fixed translate of the positive Weyl chamber. This is the statement which, in the SL2 case, that was basically the argument that I showed you before. And in general, you can reduce to Courant 1 situation. The argument is very similar. When we apply it to Eisenstein series, it gives exactly the statement that we had before. Why? Because I claim that all these exponents, they don't lie in the positive Weyl chamber. They lie very far from the positive Weyl chamber as long as lambda is positive, because mu is just some kind of little noise that you can ignore. And the W of lambda will just a basic geometric fact that for these kind of W's, out of the identity, it will take the positive chamber to very far from the positive chamber, because it's basically a fundamental domain. So this is all to it as far as uniqueness is concerned. Now, what about the locally of finite type? Well, for that, that's kind of technically a little harder. We need an additional set of equations, namely that, as in the SL2 case, that the function is an eigenfunction under some convolution operator. So the claim is that there is an analytic family of functions of compact support on GA and some scalar function Ci, which don't have a common 0, such that delta of hi lambda. So the convolution acts by scalar, which can be taken non-zero. So this kind of statement, that's part of what, it's a basic result of Harishchandra. Well, Harishchandra technically proved it maybe for one automorphic form, but the method is robust and extends to holomorphic family of automorphic forms. In fact, it's explained in the book of Mugler-Walsh-Perget, which revisited Langland's book on Eisenstein series. Anyways, this is kind of a basic fact, which I will not go over. And so now let me just detail the local finiteness statement, which I'm sorry that it's a bit hard to follow, but believe me, it's much better than when I was a graduate student. I don't want to sound like your father all the time, but it's part of the business. Okay, so so the shape of the equations are the following. So we have this. So now I just take one convolution operator equals f. So that was your question, why it's 1. So I just divide by h of s, which I can do, because they don't have a common 0. And then the other equations. So what are the other equations? I have my automorphic form. Well, a priori it's not even automorphic form. It's just function of uniform modular growth. I take the constant term with respect to maximal parabolic, so for each simple root. And then I have some polynomial in this Ta alpha. Ta alpha is just the left translation by the center. So I fix some A alpha with, let's say, bigger than 1. And I just apply. So I'm given some holomorphic family of monic polynomials of fixed degree, M alpha. And when I apply these operators to the constant term, it's 0. So the constant term satisfies some difference equations. And that's what automorphic forms satisfy, right? The constant term satisfies some difference equation like that in the center of the levy of the relevant parabolic. So these are my equations, okay? So I have this convolution equation and the equation about the constant term. And the claim is that this system of equations is locally of finite type. Is the statement homotopic to clear? Yeah.
The second equation is killing all the exponents, not just Caspital now, right?
Right.
It's that you have a way to control all possible exponents.
In fact, once I know it for Caspital exponents, well, you see, I didn't assume to begin with that it's an automorphic form. So the Caspital projection, it needs to be defined. But it doesn't really matter because once I know it for the Caspital projection, then it will be true for all the exponents. So this equation will be satisfied. You can say that it's stronger, but in fact it will be satisfied. So I can assume that this is satisfied.
In the rank 1 case, weren't you also restricting to a compact set? Why don't you do that here?
Okay, so this is just the system of equation on X itself. This is the system. To prove it, so this is the next sentence. So in order to prove it, so this is the statement. And the proof, I do this yoga with, that will be the next slide. But this is the statement. So remember also in the SL2 case, there was a statement about functions of uniform modular growth. And then in the proof, we used some auxiliary space. That's exactly what we are going to do here. So we are going to use these weighted Hilbert spaces that actually Franke also considered in his paper. And so I don't want to spend too much time on that, but I'll just give you kind of the gist of it. So again, we have a Siegel domain and we will model everything on the Siegel domain. So there is a weighted, you can put a weight on the Siegel set, depend on some parameter lambda in this A0 star. And via the pullback, so again, it's a very nice kind of embedding from S to X. I won't describe it in detail, but it's finite to 1 and it's 1 to 1 when you're far off. So it's kind of grosso modo, X and S are kind of roughly the same. So this gives rise to a Hilbert space H lambda X, which strictly embeds in H lambda of S, the Siegel set. And the function of uniform modular growth is just the union of the smooth part of these spaces. But the advantage of this H lambda that it admits a Harshano decomposition, which, as I said, is kind of a simple thing. It's not, there's nothing complicated here, just kind of very basic stuff. And so you can decompose each function according to these constant terms yoga. And so I won't go into the details, it's not worth it, and you're probably already tired anyways, but this is kind of the auxiliary system that you get. So you do the same trick that you retain the difference operators on each component, so to speak, but so each component is like the cuspidal part along P. And then in the center part of P, so this is for every P, so yeah. And in the center part of P, you only kind of truncate the center part to a compact set. So this means, what this means, that, okay, you just take off the translation. Maybe I'll just draw a picture, it will be easier. When you're close to 60, things become, your body is not so flexible. Okay. So this is just this space, right? I remove the translate here and the translate here. So, but this is just in the center of the P. Okay, and then the same thing, the claim is that the same thing happens, that you have a strict embedding and Hilbert-Schmidt. I think you've seen enough, and if not, then you can look at my notes. And let me just finish the story about Eisenstein series. So the proof gives also the functional equation. I swept the intertwining operators under the carpet because you can somehow avoid them. That's kind of the point of this proof. But because of the uniqueness principle, this functional equation will actually come up. And in the function field case, things are actually easier. You don't need to worry about Fredholm. Everything is algebraic, nice. The principle of meromorphic continuation is algebraic, and it's like smooth sailing. Okay, so Yanis asked me to give some open problems. Oh dear. So maybe the first question is, again, I'm not saying that the world necessarily depends on it, but can you somehow modify the proof that it will hold not just for K finite? Here I use K finiteness very, in a crucial way because of this Fredholm theory, compact operators. I mean, it's not going to be, if I want it to be an eigenfunction under convolution, it must be K finite. This is the way of life. But can you somehow make an argument which is applicable to smooth automorphic forms? Well, for that, if you want to use this method, there are other methods to extend from the K-finite case, but if you want this method, you will need to extend the principle of meromorphic continuation. So maybe some young graduate students can think about this, I don't know. And okay, there is another technical question about finiteness of order, which is, it's used in the converse theorem, for example, but I think that's a little bit beside the theme of this conference, as much as I can say. I'm not an organizer. Okay, let's turn to I still have a few minutes, somehow surprisingly. So let's turn to the spectral decomposition. So today I'm going to cover the kind of the core theory of Eisenstein series, and tomorrow, well, we'll see what's tomorrow. So what about the spectral decomposition? So I have the space of automorphic forms which are L2, okay, what does it mean? It means that basically I induce the discrete spectrum form of M. That's what this space is, or it's an automorphic part of this. And so this is one unitary representation of GA, and I have intertwining operators, but that's, I mean, I'm saying it nonchalantly, but of course this is a deep fact that I have intertwining operators from this AP2 to AQ2, which comes from the theory, right? Which I just described before, and because of the functional equation, they are unitary on lambda, on lambda unitary. In particular, they are holomorphic, and so they extend. So a priori, they are just defined on the automorphic part, but because they are unitary, they extend to the whole Hilbert space. So I have these isometries, which, as I said, I emphasize that they are highly non-trivial. And what the Langlands statement says is that I can build so it gives a decomposition of L2 of GA mod GF. What is this decomposition? Well, I start for any parabolic, I can look at this kind of wave packet of Eisenstein series. So I start with let's say, a compact support smooth function, and I average this Eisenstein series. It will be in L2, not before I average, but after I average. And so okay, we had groupoids last talk. So the parabolic subgroups, they form a groupoid where the morphisms are that on the level of the Levy part, it's conjugation. Okay, so all association. And so for each P, I have this representation, and So I don't know what's the terminology of groupoids, but anyways, I can take some kind of co-invariance of this groupoid, but I can just use standard parabolics, that's good enough, and then it's like almost usual co-invariance. I can, because everything is finite, I can just think of it as functions which have this symmetry.
Sorry,
Yeah.
can you explain what you said about unitarity?
Yes.
What is the...
So I was a bit fast, but right. So I have the, I have these functional equations. If I special, and also the adjoint of mw lambda is mw inverse of minus lambda bar or something. So that means that if lambda is unitary, then mw lambda is unitary. If lambda is imaginary, rather, then mw lambda is unitary.
I see, because you know that the adjoint is the inverse. That's what you're using.
Because I know that the adjoint is with the w inverse, yes. With the w, with the lambda bar, yes. So that comes from the functional equation. I was quick here, but yes. And that means that it extends to the whole L2. A priori, it's defined only on the automorphic part. Okay, so that's Langland's statement. And so I just want to give, so again, we want to revisit this. So I'll say a few words and then we can take a Q&A, I guess. Okay, so Langland proved it in this treatise of his, and it's a tour de force. And okay, I don't want to, you're not, nobody here is a student in comparative literature, so I don't want to do too much of this, but I'll just tell the story that I have. And I'll tell about a simpler approach due to the LOM, which is also can be found on the archive. Maybe it's already published now. And okay, there will be some small technical simplification if we get there. And the input for that is, of course, the Meromorphic continuation of Eisenstein series. So in Langland's case, he only deduced it at the end. He started with Caspidal, but let me not get into that. And another key idea is, again, an idea of Bernstein from the 1980s in his paper on the support of Plancherel measure. So I will explain. And the method is analogous to Plancherel formula in the local case, and there's a lot of literature there. I don't want to get into discussion here. For the sake of the discussion, I will assume that the Eisenstein series are holomorphic on the imaginary line. Well, I already said that the intertwining operators are, but it doesn't really mean just by itself that the Eisenstein series are holomorphic because there are more intertwining operators. But anyways, it can be proved using this, so let's just take it for granted. And let me just explain the ideas. So there are two notions that are important. One is the notion of tempered automorphic forms. So tempered means that somehow it's almost L2. So again, phi is automorphic form on XP. And so there are kind of two statements here. One is that the exponents, the real part is 0 along the center of P. And the other one is that somehow inside the levy, the exponents are subunitary. So it's very similar to what was in the previous talk, by the way. So this is the space of tempered automorphic forms. And that's, so the AP2 that we described before, that's totally contained because there we require that it's actually negative. And Eisenstein series carry, at least when they're holomorphic, which we assume on the imaginary part, they carry AP2 to AG temp, to temper. This is all simple. Okay, and now comes this gadget, which I don't have a good way to explain it very briefly. I mean, it's not complicated, but it just needs some thinking. So I have this temper distribution on AP. Fortunately, this notation was introduced. Thanks for Olivier for doing that. And so I have a very simple distribution, which is in fact a polynomial exponential. The exponents are governed by the exponents of phi and psi. The way I do it, I just take the constant, the inner product rather, but on the center I have to put some, let's say, tempered function. This will converge. So psi, yeah, phi is in AP2, so this will make the inner product on the M part converge, and the center part, because of the F, it will converge. Okay, so that's one piece of kind of notation that we will need, and the other one is the the weak constant term, which is analogous to the local theory. So you start with a tempered automorphic form, you take the constant term. What is the weak part? Well, you just decompose it according to the exponents of the center, and you only take the part which is real lambda 0 rather than just, the subunitary part. You just take the unitary part. This turns out to be technically very useful. And so what you get now is something in the tempered guy, because the real part of lambda is 0, the other exponents are certainly subunitary. So you make this definition in order for this to be here. Now, notice that if you started with something in the discrete spectrum of L2, then the weak constant term are actually 0, because the real parts of lambda are all negative, so you just throw them away. So this is actually 0 for all proper P. And what is important, of course, is that you don't lose. So if the weak constant term is 0, then the function is 0. I'm talking about the temper. Always the functions are tempered, but in fact, it's enough to have this exponential polynomial equals 0 for all P. So these are kind of basic factors are kind of needed. And so here comes the main statement. And basically, that's all what is important to remember, if at all. So there is some inner product formula. So you take this wave packet, excuse me, of Eisenstein series starting from, AP2, this wave packet, against some tempered guy. And this will capture somehow the whole L2 decomposition. And the claim is that it has a very simple formula, namely you kind of pick the value of f at kind of, how should I say it? Well, so what is this guy here? I said that this p phi psi p weak, whatever it is some polynomial exponential. The Fourier transform, so you can look at it as a compactly, finitely supported distribution on the dual space, and you apply it to f. So it's a very simple, so it's some kind of derivatives of f at the point which is somehow determined by the spectral parameters. And so the right-hand side is something very basic. And so this is the main claim. So this is just basically a reinterpretation of Langland's formula, of Langland's spectral decomposition. The point is that you have it for any automorphic form psi, any tempered automorphic form psi. This is meaningful because this guy is in the Harry-Chandra-Schwarz space, so you can pair it against any tempered automorphic form. And why is it so that it's equivalent to Langland's spectral decomposition? Well, because of this this theorem of Bernstein from the 80s that only tempered automorphic forms play a role in the spectral decomposition of L2. I will not, of course, prove it here, but this is, although it's post-Corvallis, but I cannot do everything. That's not my job. And so that means that in order to describe the L2, it's enough to pair. So for instance, if you want to show that these wave packets are dense, it's enough to know that they don't pair to 0 with any, so for any psi non-zero, you will get something non-zero by some choice. And that's exactly what we said before, if you remember, this property. This property and Bernstein's result tells you that once you have this formula, the wave packets are dense. And also you can compute the constant term. Maybe I will not do that. But you can compute, if you take psi, which was a priori a tempered automorphic form, if you take it to be an Eisenstein series, then you can calculate all these things, and what you get is exactly what you are supposed to get. So to make a long story short, the key statement is this statement. And, I still have a few minutes. That's maybe. So I'll just give a few more details about this key proposition. I understand that it's not so easy to digest everything, even though your metabolism is faster than mine. Okay, so the meromorphic continuation of Eisenstein series, the proof that I illustrated, I think it's kind of the proof from the book. and it's kind of the definitive proof, as far as I'm concerned. About this thing, so I don't know of a definitive proof. I know of an ugly proof. So the ugly proof is using Arthur's truncation. Maybe people will discuss it. So the Arthur truncation is some gadget which I will not define, but it somehow makes, it's some way to regularize, let's say, integrals, if nothing else. And in particular, what you can get from the truncation is some polynomial exponential. So t is, again, a parameter in this space A0. And the Arthur truncation gives you a function of rapid decay. So it's meaningful to integrate it against any function, basically. And what you get a polynomial exponential, again, and the exponents are governed by the exponents of phi and psi. So that's some basic operation of Arthur. And again, in the tempered case, the exponents are subunitary. So you get, so you can take the unitary part, which is kind of reminiscent of what we did with the weak constant term. So that's what we will need from the Arthur truncation. And so here I will not go into details, it's useless, but the point that there is a more precise formula for the inner product of truncated Eisenstein series with psi, and it's a little bit more involved, but it has kind of similar feature. And so this is explicit, but it's only for the unitary part of that expression. And once you take, so there's no point to go over that, but once you take t goes to infinity, you recover the key statement. So this is some kind of elaboration of the key statement, but okay, some people may not like, they may like Arthur, but they may not like truncation necessarily. There is some arbitrariness in this operation. The key statement, I think, is fairly robust, but this statement is a bit more. I can imagine that there's a better way to say it, but anyway, this is a way to prove it, if not the best. Okay, I will not say more about this. And okay, so, and just as a last technical thing, that you can actually write the truncation of Eisenstein series in terms of some relative truncation of kind of smaller. So there's a way to write it as sum over parabolics of smaller truncations. I will not get into details for that. Let me just make the remark that in the Caspial case, that was actually this expression here, which is simpler than what it is in the general case, but that was Langen's ad hoc definition of truncated Eisenstein series. Arthur took this expression and actually realized that you can make a truncation operator on space of all locally L1 functions on GA mod GF, and kind of reproved Langen's formula using his revised definition of truncation. But that was only for phi cuspidal, but in fact, you can do it for phi general. It's a bit more complicated, but it still has the same feature that you have some characteristic functions of not simplicial, but some cones, which you can work with. And when you put everything together, you have some Mellin transform. When you compute, everything somehow becomes what you want. So to be continued.
Okay, great. So we have a little bit of time for questions. Are there any questions? There's one over there. So I've been told that there's actually mics placed around, so we don't have to repeat questions. I don't need to come. But don't be worried. It's just you can ask your question and it will be heard over Zoom. Okay, cool. So you mentioned an open problem about Eisenstein series induced from a non-K-finite data.
Yeah.
Is the analytic continuation not known, or just not known by the method of Bernstein?
Right. So I think that certainly for L2 it is known, and I think that Wallach. Yeah. So Wallach has a way, a general statement that in this kind of scenarios you can extend from the K finite to smooth one. So I believe the answer is yes, but it's not under oath. So
Other questions?
Yeah, maybe I, yeah. So Erez, so in the local case, right, I mean, there were these two equivalent conditions of being tempered, right? One is weakly contained in L2, and the other one is a constant term, which is non-negative or something like that, right? The exponents. And you seem to mention a global version, right? You define tempered by this constant term being positive or non-negative, right? And then, so you seem to suggest that this is equivalent to being weakly contained in L2 of GA mod GF. So the question was, is this true in the same way as in the local case? I mean, this statement, what was the proof like? Is it similar to the local situation? Because I didn't recall seeing this documented anywhere.
Okay, at least somebody read, is reading it. I mean, this statement, the fact that this estimate is equivalent to something about the exponents, this is kind of standard. Whether, I mean, to say that it's weakly contained in the L2, okay, there is no explicit statement like that here, but morally it's kind of follows, but I don't want to make a precise statement like that.
Ah, okay, so you didn't say that this is weakly contained in L2 X.
No, I'm not saying that explicitly, no.
Oops. Okay. Yeah, I'm not saying that. Okay, thank you.
Okay, any other questions? Okay, then let's thank our speaker again.